Back again with your favorite operators, the raising and lowering operators. We saw last time how the raising and lowering operators were used to find a wave function. When we did that, we defined the raising and lowering operators in terms of the position and momentum operators. Now, in this problem, we will investigate how to define and use the position and momentum operators in terms of the raising and lowering operators. In doing so, we wish to find the expectation of x, momentum, x squared, and momentum squared, and of course the kinetic energy term T for the stationary state of the harmonic oscillator, using of course the raising and lowering operators. And finally, as any quantum mechanist will do, check that the uncertainty principle is satisfied. But before we can do anything with the expectations, we need to first algebraically solve for the position and momentum operators as we see here, where x is the square root, because we had some constants, of h bar over 2 m omega with the raising operator in blue plus the lowering operator in red. Momentum, of course, has to be difficult, and we have some more constants, the imaginary part, of course. And instead of the plus sign, we have a minus sign. Naturally, the momentum can't just be the rearrangement of m omega. It has to also be a minus sign here. Notice that we're going to color code this whole exercise with blue being the raising operator and lowering in red. And when they act on a wave function, this is the general form of the result with their new normalization. And again, let it be acting on a wave function. This is the new normalization constant, but let's take a quick note here that this little sub n here gets plugged into this n here, regardless of what state it is. This n on the left is the current state, and you're moving to the next upper state, or the next excited state. Here in the red, again, we're lowering from the current state to the next lower state, but note that we can only lower up into the ground state. And once we get there, we see that we will equal 0. So just be aware and handle with care. We're assuming that this is for the stationary states. We're finding it for something that can facilitate that need. Moving on though, when applying these, much like the momentum operator, we must apply the wave function. We must apply the operator to the wave function on the right. So if we plug these in, we see that the a plus and a minus, they need to act on the side to the right. And that's just the normal way of which we have written our math. And so let's see what this boils down to. Once we plug in the operator in terms of the raising and lowering, let's go ahead and kick out the constants outside the integral to save ourselves some headache. Note that because these must act on this wave function, we right distribute the wave function in. So phi sub n, or psi sub n to this and psi sub n here, which we see color coded in blue for the advancing or raising operator and red for the lowering. Of course, here, if we use the definitions we saw on the last page, we just plug in for a sub plus for the raising, n plus 1 for the lowering, n with the state below it. Cool, we like that. Now what we have to do is not only left distribute the conjugate, but we can also split up the integrals with their respective constants, which is what we do here. So we have psi star n to psi star n plus 1, and psi star n to n minus 1. Constant here from the lowering, constant here from the raising. But, you know, we see something cool here, and we note that the indices don't match, so guess what? Orthogonality tells you that these integrals are 0. How awesome is that, and what a wonderful tool to use. Speaking of wonderful tools, haven't we seen this form before? Thank you, Aaron Fest, for allowing us to calculate momentum with such ease. Let's go and get our hands dirty with the actual heart of this problem with the square operators and see how to handle that. As promised, the squares are going to be the messiest part of this, and the squares need to be handled with care. As you see, whenever we square the bracket, the constant, the square root goes away, cool, but we still have a square on the parentheses, and that needs to be FOILed out. In this case, we need to burn into our heads that order matters, absolutely matters. whenever you're distributing the raising onto the lowering, like we see here, the order of these operations matter, and in general, they do not commute. Okay, so if you reference the notes, we had the commutator relation there, and that's what this stems from. Okay, so now that we see that we had to distribute, so we multiply a plus to a plus, and then a plus to a minus. Now we distribute the a minus on a plus and the a minus on a minus, so we get a square operator there. But again, we have to apply these to the wave function on the right, and so when we distribute it, these are the four things we need: the raising operator twice, the lowering then raising on the wave function, the raising then the lowering. Again, pay attention to these two, we'll see why, and then lowering the wave function twice. Alright, so here in the first application, we see that we need to raise to the state n. So since this is squared, it's just the raising twice. So here's the second operator, here's the first operator. In this first application, we see that this is now the current state to this a plus operator now. So we need to plug this n plus 1 into the form of n plus 1. So what we have here is n plus 1 in parentheses plus 1, and that's how we get an n plus 2 here. That is what we mean by the current state is what's on the wave function being acted on, and we need to plug that number in into the end state on the right. Okay, so we see that as expected we had to raise this up 2, so we get a plus 2 in our end state. Wonderful. Now we have to be careful because we have to lower it first. So our current state is in, we plugged it in, cool. Now the current state is n minus 1, and because we're raising, we need to plug n minus 1 into the n of the form, which is what we see here in the parentheses. So if we plug n minus 1 in here, we see that the minus 1 and plus 1 cancel, so we get a root n times root n, but because we minus and rose, we're back to the state of psi n. Cool. Similar here, what we see is that we have to raise it first, so our current state is n, so n goes into the n plus 1 right there only, and then we add 1 to it, so now our current state is n plus 1. So when we lower, our current state is n plus 1, and we have to plug that into n in the n formula, so that's why we have a red n plus 1 here. But again, since we rose it and then lowered it, we go back to state n. Note here how the coefficients here are not the same, although we raised and lowered in a particular order. Again, this tells us that order matters. Here I get the root n times root n. Here I get the root of n plus 1 squared. So these orders do matter, and we'll see that is a high importance later. Lastly, we want to lower it twice, so we lower n to the state n minus 1, so we have to plug this n minus 1 into the n form, and we get n minus 1 there. Again, lowering it twice brings us to n minus 2, so everything is checking out on par, and let's see how we clean up the integrals. So with that, what we see here is that once we plug it all in, and we substitute these in and distribute, notice that we get to use our old friend again. Which old friend? That's right, orthogonality. Are we noticing a trend here with these orthogonal state solutions? They're wonderful, aren't they? With that being said, what we have is a redundance of coefficients left over. Note that it's the intermittent pairs of the raising and lowering that bring us to the same state n. So we have n squared in the root here. That goes down to n here. We have two n plus 1 terms, so that goes here. And of course, we get to consolidate this down, factor out a 2 via force factoring, and we see that we have n plus 1 times h bar over m omega. Pay attention to this coefficient in parentheses. This will be a statement that everyone will know with the harmonic oscillator. Moving forward and using a very similar method, just changing the coefficients for the momentum coefficients and the signage due to we have a minus sign in between the operators versus a plus sign, we get a pretty similar result. See, distributed out, again, order matters since we have a minus sign here and here instead. So we have a minus sign on our brackets. Again, pretty similar, easy enough to handle. And then when we factor it all down and simplify it, we see that we once again get an n plus 1/2 times some h bar m omega. This parentheses keeps coming up, and it happens for the harmonic oscillator. Of course, you know that the kinetic term uses the p squared term, which we saw last time as well. So plug that in, cancel away appropriately, and you see that we get 1/2 of the n plus 1/2 times h bar omega. Note again here that this proves that half of the energy came from the kinetic term and half of the energy came from the potential term, and that is a very cool fact to see here once again. We saw it last time in the big chart. Now we see it in a redundant statement in a new way, so pretty cool to verify that. On to the standard deviation, or the uncertainty in x and p respectively. These are calculated as we expect, where we have the square root of the square expectation minus the expectation square. Plug it in, we see that this was 0 and this was 0, so we don't include them. But what we see is that we have an n plus 1/2 times h bar over m omega, and we split this up for the convenience of what we will see in the product of these two. Same thing here, n plus 1/2 times h bar m omega. When we multiply them through, we see we can color code out blue to blue for x and red to red for momentum. But both of them have an n plus 1/2, and that's why we see inside the parentheses, or rather inside the square root, we have the parentheses squared, gone to green. Here, of course, if we have a fraction of m omega times an m omega, they cancel out beautifully, leaving us with the square root of h bar squared, and of course that will come out. So their product yields n plus 1/2 h bar is greater than or equal to h bar over 2, the uncertainty limit, for all n in the positive integers. And this is ranging from 0 to positive infinity. Again, n can be 0 for the harmonic oscillator versus the other ones where we need n equal 1. Pretty cool, but again, you see the importance of that n plus 1/2 in the whole theory of harmonic oscillators. So that's a great way to check yourself. As always, until next time, happy learning.